So what we are going to talk about today is capacitance and capacitors. And this is going to be extraordinarily similar to what we talked about on Wednesday. So let's first define what a capacitor is. The most simple form of a capacitor is what's called a parallel plate capacitor, in which we have two parallel plates of material like so, containing electrodes. And we have some physical dimensions that we'll need to pay attention to a little bit. So let's call this dimension the width of the plate. Let's call this dimension the length of a plate. And then let's call this dimension D, where D represents the gap between the plates. Okay. Now, traditionally, these two plates are separated by an insulating material called a dielectric. So I'm just going to fill in this area with red stuff representing our dielectric medium. So this dielectric medium can be a variety of different materials, okay? It can be air or a vacuum, so it can literally be nothing, and it still it counts as a dielectric medium, okay? Dielectric materials have what's called an electrical permittivity that is based on a fundamental quantity of physics. So for a vacuum, we have what's called epsilon naught, the permittivity of free space. That is 8.854 times 10 to the negative 14 farads per centimeter. And every other material is measured relative to that permittivity of a vacuum. So for instance, the permittivity of air is like 1.001 times the permittivity of free space. The permittivity of silicon is around 16 times the permittivity of free space. The permittivity of deionized water is about 81 times the permittivity of free space. So everything is measured with respect to this permittivity of a vacuum. All right, so we have a top plate and we have a bottom plate like so. So now let's talk about what a capacitor does. So capacitors are used in electrical circuits as a different form of temporary energy storage, right? So they are fulfilling a very similar role to that of an inductor, but the mechanism by which they store energy is very different. If you recall from Wednesday's lecture, inductors store energy in the form of a magnetic flux that's concentrated inside of the coil. Well, capacitors store energy due to a concentrated electric field between the plates. Okay. So what's going on is that the plates of a capacitor are used to collect electric charge. So if we were to apply a potential difference across the terminals of a capacitor and it was completely uncharged, what we would see, so let's say that I'm applying a voltage with this polarity, okay? And let's just call it a DC voltage for now. So what we would see is a positive charge carrier. Well, really, it's actually an electron in the metal that makes up the plate, but we're going to treat it as if there were a positive charge carrier. So we would see a positive charge carrier get pushed until it sits on the plate, and that would draw a negative charge carrier to the negative plate. So for every individual positive charge that we accumulate on the top plate, we're going to attract a negative charge to match that, so that it's always perfectly balanced, okay? Well, because positive charges repel each other and negative charges repel each other, every additional charge that we store on one of the capacitor plates makes it a little bit harder to store another one. And so what this is going to look like is, over time, here's the voltage drop across the capacitor itself. And this is time. What's going to happen is we're going to see that it takes time for us to charge the capacitor. And at first, the slope is very large because it's easy to put more charges on. But as we accumulate more and more charge, it tends to flatten out. Okay. So this actually looks like 1 minus e to the negative alpha c, where, I guess actually, let's call this V naught, where V naught is the voltage that it settles to over time. Okay. So what's really interesting about this device, or at least really interesting to me, we have a top plate and a bottom plate separated by an insulating material. What is an insulating material? What does that mean? You guys learned about insulators, semiconductors, and conductors on like the first day of Engineering 120. What does it mean when you have an insulating material? Right, doesn't allow electrons to flow. So how do we get current to flow in a capacitor when there are two plates that are physically separated, meaning that there is no contact or no path for current to flow through? Well, it's all about moving charge on and off the plate, right? So once we, let's say it's going to take some amount of positive current to push charge onto the plates. Well, if we let the charge move off of the plate, that constitutes a negative current because the charge carriers are moving in the opposite direction. So instead of having a real current like you and I would think of charge carriers passing through an element, we have what's called a displacement current, where we are putting charges on the plate and then allowing the charges to move off the plate, and that's where the current comes from. So there's no actual transfer of charge carriers from the top plate to the bottom plate, or vice versa. We're either putting enough energy in to force these carriers to stay on one plate where they don't really want to be, or allowing them to move off the plate, and that's where our current comes from. So the charge that's stored on a plate represented by symbol Q, is equal to the capacitance of the plates, C, multiplied by the voltage that we apply to the plates. And so from this relationship, we can define capacitance C as simply the ratio of the charge stored on the plate divided by the voltage that we apply to put that charge on the plate. So this is the ratio of the change in electric charge due to a corresponding change in voltage. The units of capacitance is the farad. Symbol F, where a farad is defined as a coulomb per volt, which is the same thing as an amp second per volt, or a second per ohm. So capacitance is largely a geometrical quantity. Depends on the geometry of the plates and the material that's present between the plates. And that relationship is given by C is equal to epsilon WL over D, where this epsilon here is just epsilon naught that we talked about previously, multiplied by what's called epsilon R, the relative permittivity of the medium that's between the plates. So earlier when I said that deionized water had a permittivity that's 81 times higher than that of a vacuum, then the relative permittivity of deionized water is 81. Silicon has a relative permittivity of around 16. Air has a relative permittivity of around 1.001. So it's just a scaling factor multiplied by that permittivity of free space. Okay. So epsilon represents the material properties that mess with capacitance. W times L is simply the area of the plate, and D is the separation between the plates. So if we want to make a very large capacitor, we would have to have a combination of a very large plate area and a very small gap between the plates. Typical values for capacitors that are used in simple electrical circuits are on the order of picofarads to millifarads, where a millifarad would be considered a very large capacitor, okay? In order to get a capacitor, a capacitance of like 1 farad, those do exist in industrial applications, and they are huge. Like they're the size of probably Dr. Long's office across the hall. They're very, very large devices. And it's because the relative permittivity is 10 to the negative 14 farads per centimeter, right? So we need a really, really large area in order to accommodate actually getting 1 farad of capacitance. All right, so let's talk about circuit characteristics. And we will start with a schematic symbol. We're actually going to have two here. We're only going to use one in this class, but I'm going to talk about the other one that you may see. So the schematic symbol for a capacitor is a pair of parallel plates with wires coming off of them, because that's exactly what a capacitor is. Okay. Capacitors obey the passive sign convention. So if we have a capacitor voltage VC of T with this polarity and a current IC of T flowing in, then so if current flows into plus terminal, the capacitor is absorbing power. And if current is flowing the negative terminal, then the device is applying power. This is the generic representation of a capacitor in a schematic diagram. Okay. The other potential symbol that you might see is this guy, where we have one vertical plate and then one curved plate. This guy represents what's called an electrolytic capacitor. In an electrolytic capacitor, where this is the positive polarity terminal on the left, and then the negative polarity terminal is associated with the curved portion. Here is our current IC. Here's our capacitor value C. So in an electrolytic capacitor, these devices are polarized. So they have a very fixed polarity. If you were to apply a voltage of the wrong polarity, they will actually physically rupture. So if you ever open up, say, a computer or something like that, and you see those big cylindrical looking things inside, and the top is domed over instead of being perfectly flat, that means that you've burst one of your electrolytic capacitors. It happens only when they have voltages that are applied with the wrong polarity. In this class, we're going to treat every capacitor as a general capacitor. And in all of our laboratory experiments and things like that, we're only going to use non-electrolytic capacitors so that you can't accidentally break things by plugging them in backwards. So just as a heads up. But electrolytic capacitors are used in a wide variety of electronics applications. So for those of you that go further into this stuff and start designing things, you will have to actually pay attention to the polarity of your components from time to time.
Yeah, electrolytic capacitors have a longer leg or something to denote their polarity.
So physically, typically speaking, they're in a canister-like package. So it's a cylindrical packaging, and it has a picture of the schematic symbol on that packaging to let you specifically know what type it is. So just as a very, very quick thing here, okay? A non-electrolytic capacitor typically looks something like this. You have a circular package, and then you have two leads coming out, okay? And there's usually some writing on the capacitor itself indicating the brand, if there's enough space, because some of these little circular things are, you know, the size of, I don't know, maybe a millimeter or two in diameter. So there's not a whole lot of room to print things, but this is typically what a non-electrolytic capacitor would look like. For an electrolytic capacitor, they'll usually be packaged in a cylinder, two leads coming off of it, and there's pretty much always space on the cylinder to write things down, and there's usually literally a description that has that symbol on it, letting you know that it is an electrolytic capacitor. and there will be a plus sign associated with the positive polarity terminal and a minus sign associated with the negative polarity terminal so that you can't accidentally screw it up if you're actually paying attention. So did that answer your question? Okay. All right. So let's get into our mathematical relationships. Okay. Electrical current, I, is defined to be the derivative of charge with respect to time. That's a relationship that we developed on the second day of class. And the only change that I've made here is I'm using the subscript C to denote now we're talking about the current flowing through a capacitor, which will be the derivative of the charge stored on the capacitor with respect to time. Well, since we know that charge in a capacitor is related to voltage, this simply becomes C dV by dt. So here is our first mathematical relationship. And as I mentioned on Wednesday, this is effectively the exact same relationship that we saw between current and voltage in an inductor, except that the current and voltage have traded places, and we now use capacitance instead of inductance. Okay, so the same basic relationship, but the roles of current and voltage have switched place. From that, we should expect to see two similar results from our derivative-based relationship like we found with inductors. Okay, so the first, if the voltage is not changing, what's the current flowing through the capacitor? 0. So in a DC circuit, capacitors behave like open circuits, right? Because in order to force the current to be 0, we have to have an open circuit. So this is kind of an equal and opposite relationship to what we saw with inductors, right? In a DC circuit, an inductor behaves like a short circuit, and a capacitor will behave like an open circuit. Without doing too much derivation here, what would we expect to happen if the voltage across a capacitor changed abruptly? So changed instantaneously from, let's say, 0 volts to 1 volt. What would the current have to be? Infinitely large. Can you create an infinitely large current? Well, of course not, because that would mean that you are creating charge out of nothing, violating the law of conservation of charge. So that means that the voltage drop across a capacitor cannot change abruptly, which goes in line very similarly to what we observed about inductors on Wednesday, where we said that the current flowing through an inductor cannot change abruptly because it would cause an infinite transfer of energy. So we can manipulate this equation. So instead of knowing what the current is or being able to define the current in terms of a known voltage, we can work it the other way around and figure out what the voltage is in terms of a known current. And so that equation is going to be Vc of t is equal to 1 over c times the integral from -infinity to t of IC T prime dt prime, or we could call this 1 over C, the integral from T naught to T, IC of T prime dt prime plus VC at T naught. This is equation number 2. Again, it is exactly the same as we observe for inductors, except that we've swapped the I's and the V's and we've replaced all of the L's with C's. The power absorbed by an inductor is IC times VC. And we can substitute in our relationship for IC to express IC in terms of the capacitor voltage, which gives us C VC dVC by dt. We now have equation 3. And lastly, the energy stored by a capacitor. So we can derive it using an integral like we did, integrating the power like we did for the inductors. But I would challenge you guys to tell me what it is based on this concept of duality, where all of our equations are going to be exactly the same, except that we swap I and V and replace all our L's with C's. So what was the energy stored in an inductor? Go back to your notes from Wednesday. 1/2 Li squared. So Dylan, recognizing that, what do you think the energy stored by a capacitor should be? Exactly right. 1/2 C V squared. Using literally the exact same derivation that we saw on Wednesday, we could get this result as well. So these are our 4 capacitor equations. They are identical in form to what we derived on Wednesday for inductors, okay? So I truly mean this. You really don't need to memorize 8 equations. You just need to memorize 4, either everything for capacitors or everything for inductors. If you understand that to go from one element to the other, you simply swap voltage and current and then replace everywhere you see inductance, you replace it with capacitance, or everywhere you see capacitance, you replace it with inductance. They are literally the exact same relationships. Davis, do you have a question? So they're both used for energy storage. They're used in effectively the same role, and it's because they behave so similarly. I would say that in practice, capacitors tend to get used more than inductances in, I'm going to call it simple electronics. And the reason for that is the tolerance value on a mass manufactured capacitor is usually better than the tolerance value on a mass manufactured inductor. So they behave more like you would expect them to behave, which means they get used more often. That's pretty much the only reason. Now, I say that, but the induction motor, which is really beyond the scope of this class to really get into great detail on, is probably the most widely used electrical device in the world. The induction motor revolutionized industry. Without that, we would not have the life we currently live, because that is responsible for how we distribute power in effectively every civilized part of the world, how we run production lines, how we heat and cool our homes, how we wash and dry our clothes. They are literally everywhere. If Nikola Tesla hadn't have given George Westinghouse an out to stop paying him on his patent, he would have had pretty much all of the money in the world by the time he died, because we use induction motors so much in so many different applications. But that's
Wait, if Tesla hadn't what? Can you repeat that?
as a component itself, capacitors are typically used more so than inductors. But inductors have a very, very large role to play in our post-industrialized society. Okay, so let's talk about how we can combine in circuits that contain multiple elements. So let's first consider a network that contains multiple capacitors connected in series. So let's say that we have a capacitor C1 over which a voltage drop, let's just call it V1, occurs. And then a capacitor C2 over which a voltage drop 2 occurs. And then a capacitance Cn over which a voltage drop Vn occurs. So let's say that the voltage drop over all of our capacitors connected in series is V of t, and the current flowing through all of our capacitors is I of t. Well, if we apply Kirchhoff's voltage law around our loop, we'll find that V of t is equal to V1 plus V2 all the way out to the end. We can express all of these voltage drops in terms of the common current that's being carried by all of the elements connected in series. So that's going to look like 1 over C1 integral from negative infinity to t of I of t prime dt prime plus 1 over C2 integral from negative infinity to t of I of t prime dt prime all the way out to 1 over C sub n integral from negative infinity to t I of t prime prime. Since we have all of those integrals are representing literally the exact same thing, we can treat this as 1 over C1 plus 1 over C2 plus all the way out to 1 over Cn of the integral from negative infinity to t of I t prime dt prime, or 1 over the equivalent capacitance integral from negative infinity to t I of t prime dt prime, which means equivalent capacitance is the reciprocal of the sum from I is equal to 1 to n of the reciprocal of the capacitance values. Or in other words, less math speak, capacitors in series combine like resistors in parallel. if we have several capacitors connected in parallel. So let's call this C1, and it's carrying a current of I1. A capacitor C2 carrying a current of I2, and a capacitor C sub n carrying a current of IN. Like so. Where the total voltage drop is V, and the amount of current passing into the parallel capacitor network is I. Applying Kirchhoff's current law, we would have I of t is equal to I1 plus I2 plus I sub n. We can express all of these currents in terms of our total voltage V. So that would be C1 d by dt plus C2 dV by dt all the way out to Cn dV by dt, or C1 plus C2 all the way out to Cn and dV by dt, which we could represent as CEQ dV by dt, where CEQ is simply the sum from I is equal to 1 to n of C sub I, or capacitors in parallel combined like resistors in series. All right. There is one last thing that I would like for us to do before I stop talking, and it is to work one of your web work problems for homework set number 12, because it's difficult for sure, but it's also one of my favorite problems, and I'm telling you very explicitly, I like to put problems like this on the exam. Really only just one, because it takes a minute to work, but I'm giving you fair warning. Let's see what chat says. Good to see you're listened to. I don't know what that means because
I just said something earlier and I wasn't heard.
Did you unmute yourself when you said it? Because
Yeah, I did. But it might have been while you were talking. I had just asked for you to repeat the thing that Tesla did that, I don't know, you said if Tesla hadn't done this.
okay, so what he did, so just as a very brief aside here, what Tesla did was he had an agreement with George Westinghouse to where he was paid a certain amount of money for every individual induction motor that was sold. Paying Tesla was bankrupting the Westinghouse Corporation. And so Tesla let Westinghouse off of the hook. He effectively allowed him to break the contract that was giving him so much money and funding all of his research.
I see.
Yeah. All right. Why is my keyboard? So homework 12, I think it's problem 3. It is not, although this isn't a bad one to look at either. This is the one. Homework 12, problem 5. All right. So I'm going to copy this down. We have, I believe it was a voltage source. Let's look, yes. Voltage source, Vs of t. Connected in parallel to two capacitors. One is an 8 millifarad capacitor, and one was a 24, I think. Sorry. 24. And these are connected in series, or excuse me, connected in parallel. An inductor having a value of 20 millihenries. So the information that we are given is that our source voltage, Vs of t, has some value. I'm just going to call it V naught e to the negative alpha t. And we are told that our source current, which is this guy right here, at t is equal to 0, has some specific value, which I am going to call IS naught. We're going to solve this symbolically. Okay. And our ultimate goal in this case is to determine IS as a function of time. This seems to be a relatively straightforward problem, but it can be a little difficult, okay? So the first thing that I would do in approaching this problem is I would combine those two capacitors in series into a single capacitance. So if we have an 8 millifarad capacitor in series with a 24 millid capacitor, what's that going to look like? 8 times 24 over 8 plus 24, which is 6. By all means, verify it. By the way, I can't do that in my head. I've just done this problem so many times. I know what that's going to be. Or I can't do it in my head that quickly, I guess, would be a better thing. But anyway. So we have a 6 millifarad capacitor. All right, so that's one simplification that we can make right off the bat. So what I'm going to do here is I'm just going to make a simple observation. I'm going to call this current IC of t, and I'm going to call this current IL of t. Our goal in this problem is to determine the quantity IS of t. And so I posit that IS of t is simply the sum of the capacitor current and the inductor current by Kirchhoff's current law. Does anybody have any problem with that? That is a relatively straightforward observation here, right? Well, we know that our capacitor current is C times the derivative of our capacitor voltage. And we know that our inductor current is 1 over L times the integral from T naught to T of our inductor voltage plus the initial condition on our inductor. Okay. So What's the capacitor voltage here? It's not a trick question. Vs, what's the inductor voltage? Vs of t, absolutely right. So I'm going to go ahead, just real quick here, I'm going to replace this C with an S. I'm going to replace this L with an S, like so. So I feel pretty, oops, don't know what happened there. Feel pretty strongly that you guys can probably take the derivative of that exponential function. And I feel pretty strongly that you guys can probably integrate that exponential function. So I would argue that this bit right here isn't particularly difficult to determine if you're paying attention to units and things like that. This bit right here also isn't very difficult to determine if you're paying attention to units. It's really just the math that we did on Wednesday, okay? But what about this guy right here? Where does that come from?
So IS do not is the value you got, but
That's not IS.
that would be split up at, wouldn't it be split up at that the inductance? So like it's not, it's like whatever your initial value is, that's not the initial value of the current going through the inductor.
That's correct.
Yeah.
Yeah. So the observation here, what I've seen, the overwhelming majority of students, what they do is they just put in the value for IS at 0 and call it a day, and then get it wrong, get frustrated, and stop working. And the reason why that's wrong is because the inductor current and the source current literally aren't the same things, right? So we've got this relationship here. By applying Kirchhoff's current law in general, I would argue that IS at 0 has to be equal to IC at 0 plus IL at 0, meaning Kirchhoff's current law has to be valid at all points in time, which must be true because Kirchhoff's current law represents the law of conservation of charge for circuits, right? Well, IS at 0 was given to us. How do we figure out what IC at 0 is? Plug in T is equal to 0 for this guy right here. And then the only unknown quantity we have left is IL at 0. So we solve for this and then plug it in here. So those are the steps that you would take in order to solve this problem. It is not intuitively obvious, so I just wanted to give you guys kind of a heads up. Problem 3 is similar, except that you're going to have a KVL relationship because all of the elements are connected in series, as opposed to the KCL relationship that we dealt with in problem 5. And I believe this one to be a little bit easier than problem 5. But anyway, I just wanted to give you guys that heads up. To curtail, I'm sure, about 15 emails for those of you that try to do your homework. Awesome.
I noticed on problem 5 they have AC voltage source.
Yes.
I thought there was capacitors behave differently in your AC voltage sources than they do DC, or am I mistaken?
No, you're 100% right. But to a DC voltage source, a capacitor is just an open circuit For anything that isn't a DC source, it's the relationships that we developed today in class.
Okay.
Yeah. So only specifically for a DC source do they behave in one particular way. They look like an open circuit. For any type of source that has any type of time variance to it, the derivative and integral based relationships that we developed today are the correct relationship. Davis.
So that source was a DC current source, and basically being open circuit.
Yep, absolutely right. You're 100% correct. So speaking of that, homework 11, I think problem 1, which I haven't gotten any emails about, which means you guys probably haven't started on it yet, contains, let's look at that real quick. This awful looking circuit containing lots of inductors. Well, since voltage source V1, V2, and V3 are all DC voltages, all those inductors are simply short circuits, which means this is just a nodal analysis or mesh analysis problem that you could have worked before we got into this set of material anyway. The only difference here is that you have to know that an inductor looks like a short circuit when you have DC excitation sources. Let's just look through a couple other things here real quick. You're given a graph and you want to know, let's see, this graph is current and you want to know voltage. So it's just going to be the slopes. So that's easy enough for A and B. The power is find the voltage at that time and then multiply it by the current at that time, read directly off the graph. And then the energy is you read the current directly off the graph and apply it into the energy equation. So that's not particularly difficult. Problem number 3 looks real similar to in-class assignment stuff that I made you guys do. Problem number 4, you're asked to find the voltage drop Vn as a function of time. That's just going to be applying Kirchhoff's voltage law around the loop. So the voltage Vn will be the voltage drop over the 10 ohm resistor plus the voltage drop over the 5 Henry source, where you have to use Ohm's law to get the voltage drop over the resistor and the derivative based voltage relationship to get the voltage drop over the inductor, and then just add the two things together. Problem 5 is a KCL based problem. IN is the sum of the resistor current and the inductor current, very, very similar to the previous problem. And then just to go through 12 in full, I guess. Really similar to the in-class assignment problem that you're about to start. Combining inductances, nothing wild or crazy there. Problem 3 is a KVL-based relationship problem. Problem 4, you're given a graph of the voltage, and then you need to determine current. So that's a derivative-based relationship. Power is current times voltage, and then energy is read the voltage off the graph and put it into the equation. And then problem 5 we've talked about at length. So any questions regarding your homework sets over this material? All right, I know this sounds wildly early, but we're actually over halfway through for the material that's going to show up on the next exam. We really only have one more topic to cover, but it takes 3 days to cover it, and it's what's called transient analysis of RL and RC circuits. In order to be successful at that, you fundamentally need to understand at a minimum the voltage and current relationships for capacitors and inductors, particularly paying attention to the fact that the voltage drop across a capacitor cannot change abruptly and the current flowing through an inductor cannot change abruptly. Everything that we're going to do for literally the next week and change is really based around those two observations of those derivative based relationships. All right, that's enough out of me for today.